in this situation, what we have is we have an unidentified compound which contains silicon, chromium, and oxygen. And we've been asked to figure out, well, what's the empirical formula of it? And we've been presented the percentage abundances in the question. Right, now, in this case, what I'm going to do to start off with is I'm going to just take a look at what the percentages given by mass in the question. What's the total? And this is just a quick check to understand, well, is it 100? Is it roughly 100? Just to understand that if we do choose to make assumptions later on, what's the underlying reality compared to those assumptions? Okay, so 65.04, and that's going to be added to 15.67 plus 19.29. And if you have a go at working that out, you should find that that comes to 100, right? And as we mentioned, we're looking for the empirical formula. We're looking for the simplest whole number ratio of these elements as it relates to this particular compound. So in order to solve for that, we really need to look into the amount of substance. And in order to do that, we're going to need to convert this into moles somehow. And so the way we're going to do that is we're going to make an assumption. We're going to assume that our sample is a 100 gram sample, and we are effectively going to, based on that assumption, we're going to convert all of these figures we have to masses. I'm going to say, well, it's for example 65.04 grams, etc., etc. And that's going to enable us to take a step towards being able to convert it later on to moles. So let's go ahead with that process. So this is therefore going to be 65.04 grams, and that's for silver, so that's going to be Ag, right? And then we're going to have for chromium, which is Cr, we're going to have 15.67 grams, and for the last one, oxygen, we're going to have 19.29 grams, right? And what we are effectively going to do is we're going to need to convert this now to moles, right? So what we're going to use is the equation that relates moles and mass and molar mass, right? So that is that the mass in grams is equal to the moles n, I guess you could put that m, it should be an mol, mole, multiplied by the molar mass mr, which is going to be in grams per mole. So, and of course, when we rearrange this by dividing both sides by the molar mass, right? So divide that by mr, divide this by mr, what we get is effectively that the moles n is equal to the mass divided by the molar mass, right? And so we're using this equation. We've got our masses, right? So we've got our masses. We're going to divide them by their respective molar masses, and we're going to get the molar masses from the periodic table. Though for, I think in the case of oxygen, you probably know that the relative atomic mass of oxygen is 16, right? So okay, so I've got some excerpts from the periodic table here, some of the relevant excerpts, and as you can see, as I mentioned, we've got silver, so Ag, right? So we've got the relative atomic mass, and then Cr, where is it? So Cr, right? And oxygen, right? So just for convenience, I've got them listed over here as well. But in this case, let's just list these next to our question. So let's just put here that the MR, molar mass of Ag, is equal to 107.9. The MR of Cr is equal to 52.0, and that the MR of oxygen is equal to 16.0, right? So that's simply, I've just got these from the relative atomic masses from the elements in the question. Okay, so now that we've got those molar masses, we can effectively use those to establish a molar ratio. So how are we going to do that? Well, we're going to divide these, as the equation shows. We're going to divide these by the molar masses, right? So 65.04, we'll divide that by 107.9, 15.67, we're going to divide that by 52.0, and 19.29, we're going to divide that by 16, right? And when we do that, what are we going to get? Well, I'd invite you to have a go, see what you get when you calculate all of these. I'm personally going to be putting the giving things to 5 decimal places at this stage. So that for Ag, for silver, what we're going to get is 0.60278, right? And so that when we do the chromium one, you should get 0.30135, and when you do oxygen, you should get 1.20563. Okay, and following on from that, we're going to take a look at now, well, we are looking for a simplest whole number ratio, right? But here clearly we do not have whole numbers. We have effectively decimals which are not that easily roundable. I mean, even if we round all of these to 2 decimal places, none of them is going to come to a whole number, right? So what we're going to do at this stage, in order to get at least 1 to a whole number, is we're going to divide all of them by the smallest number. And in this case, the smallest number is the 0.30135 that relates to chromium. So let's go through that process now. So 0.30135, right? And what does that give us? Well, that is going to give us effectively, so for the Ag, we're going to get 2.00027, right? Now for chromium, we are dividing a number by itself, so of course we don't need a calculator really to know that that's going to just give us 1. And for oxygen, if you calculate that, what you should find is that gives 4.00076. Okay. Now, what you notice here is that we've now got at least one value out of these, which is a whole number, right? The one that we divided by itself. The other two are not whole numbers yet, but if you pay very close attention to the numbers, what's changed when we compare it to when we were at this stage above, for example, like 0.60278 and you know, all the others anyway, actually, you notice that now if we apply the same heuristic, if we say, okay, but I want to know if we round all of them to 2 decimal places, are we going to get integer values? Previously, the answer was no. If we did that, we're not going to get integer values. But if we have a go at that same process now, right, what are we going to get? Well, we're going to get 2.00. And then, of course, this is already at, you know, it's just a 1, right? So, and then in this case, if you do the same process, we get 4.00, right? So when I rounded them to 2 decimal places now, we've got all integer values. And if we look at this from a perspective of, well, is this divisible by anything? To get a more simple whole number ratio, if we look at the 4 is divisible by 2. 4 is divisible by 4. However, when we look across the board, the same cannot be said for and this is specifically in relation to looking for what can result in a whole number, right? 1, if we divide it by 2, we're not going to get a whole number. If we divide it by 4, we're not going to get a whole number. So overall, this would be our simplest whole number ratio. And in this case, that means that for AG, we're going to have a 2, right? For CR, we're going to have a 1. And for oxygen, we're going to have a 4, right? And of course, in our final formula, really, we don't need to put the 1 there. That's not, it's not necessary. So what we're just going to have is A, G, C, R, O, 4. And this, in this case, is going to be our simplest whole number ratio. So this is the empirical formula. Now, this particular formula has some quite interesting things about it, I would say, right? This formula is actually the formula for silver chromate, right? So silver chromate, right? And what I've got actually is a bit of a, let's look over here. Silver chromate. So if you study biology, you may have heard of the Golgi apparatus in cell biology, right? And effectively, as part of the person this was actually named after, Golgi, is this scientist, Camillo Golgi. He's an Italian scientist. At the time that he was around, or at least at the time when he was awarded his Nobel Prize. Here we have actually, this is the state flag for Italy at that time. It's changed since then, but that's what it used to look like. And he was awarded the 1906 Nobel Prize for Physiology or Medicine, and part of it actually relates to that silver chromate which we just looked at, in the sense that this is actually one of the things which played a role in staining of nervous system tissue. So his actual Nobel Prize related to his work on the central nervous system. And one of the things he did is he actually devised a method. It's called Golgi's method. And his method effectively, part of it involves silver chromate. It's specifically in relation to staining of, so it's effectively creating a contrast in nervous system tissue, so that you can kind of basically study it a bit more easily, right? So he derived that method. So the method's effectively named after him. It has some other names, but yeah. So obviously, as you can imagine, there's quite some important scientific work. But this is just some information about silver chromate. One of the other methods, which actually silver chromate has some relevance to, which in the context of chemistry is perhaps closer to home than staining of nervous system tissue, is titration. So titration, not all titration, but there's a specific method within titration called the Mohr method. So that's MOHR, Mohr method. I'm not going to go into details about this method, but I would encourage you, if you feel like doing so, take a look at what the Mohr method is about, what it's for, and how it perhaps relates to silver chromate and silver ions as well, and titration. Okay, so but long story short, the empirical formula in this case is, as we saw, was Ag2 CrO4. I actually didn't put the 2 there. I completely, okay. Yeah, at least I checked it. So yeah, so the empirical formula in this case is, yeah, Ag2CrO4. Okay, all right.